Okay, so this question is all about carbocation rearrangements. We've got an alcohol and a strong acid, and so we're going to form a carbocation, but that carbocation may not be stable and may rearrange before it combines with a nucleophile to give the product. So the first thing we're going to do is we're going to draw out the acid to make it easier to see how the protonation step occurs. And we're going to put the lone pairs of electrons on the heteroatom, the oxygen. Okay, so the first step is going to be that we get protonation of that alcohol to make it a better leaving group. And so even though this question is really just asking for what is the product, we're going to need to sketch out the whole mechanism so we can see what that product will be. Okay, so there's our 5-member ring, untouched. Here's our alcohol. Now we've got a second hydrogen on there now, and it's got a positive charge because the oxygen's used its lone pair of electrons to form a new bond to that proton. Okay, and then there's the rest of the molecule. Now we're going to form that carbocation, so let's do that next. So we're going to break that bond between the oxygen and the carbon, and we're going to kick out water as the leaving group. So if we wanted to, we can write minus H2O over that arrow. And the carbocation we formed is a secondary carbocation. And we know that they aren't particularly stable. So if it can rearrange to something more stable, it's going to do that before it does anything else. Okay, so that's a secondary carbocation. So next door to that carbocation, we've got 3 alkyl groups. We've got this methyl group here, we've got this part of the ring, and we've got that part of the ring. So any one of those 3 groups can migrate and form a more stable carbocation. So in this question, we're not just being asked, can we spot that a carbocation is formed and that it rearranges, but what will it rearrange to? So we've got a choice between a methyl group here migrating or one of these groups over here. So these groups are part of the ring, but if we look at each one, they're primary groups. So they will migrate in preference to the methyl group because they have a better migratory aptitude. There's also the bonus that we go from a 5 to a 6-membered ring if we migrate one of those groups. So 5-member rings are pretty good, but 6-membered rings are even better. We have even better bond angles in a 6-membered ring than in a 5-membered ring. So given the choice, we're going to see a primary group migrate in preference to a methyl group. So let's draw that migration. Now the ring's symmetrical, so we can pick either one of those bonds. And I quite often like to draw in the pair of electrons that's in that bond, put a circle around it, and show that migrating across to the carbocation center. So see that arrow starts with a pair of electrons and it ends up at the carbon to which it's now bonded to. Now another thing that's useful to do in these sorts of reaction mechanisms is to number the system so that it can follow exactly where bonding is in the product relative to starting material. Okay, so if I just start numbering at the carbocation, 1, 2, go around the ring like this. What we want to do is draw just the ugly structure first. So draw it just like it's drawn in that starting material, like starting carbocation, but with the new bonding arrangement in place. So I'll show you what I mean by that. So as this rearranges, we're going to have something that looks very similar to what we had before. Okay, we can put our numbers in. 1, 2, 3, 4, 5, 6. But now in the product, it's the number 6 carbon that's bonded to the number 1 carbon. So we can just draw a line between those two to show that there's a bond, even though the structure looks really ugly. Okay, we can redraw that to make it look prettier, but at the moment I just want to make sure that the right atoms bonded to each other. Now, a big stumbling block for many students is knowing where is the charge left over after I've done this migration. So after I've done the migration, the bond is migrated from between the 6 carbon and the 2 carbon, the pair of electrons is now still between the number 6 and the number 1 carbon. So the number 2 carbon is now missing a pair of electrons that was in that bond. So it's going to be the carbon that has the positive charge, and it's going to be the carbocation. And we've done this rearrangement because that's now a tertiary carbocation. Okay, so we want to redraw this in a much more aesthetically pleasing format. And so what we have to do is recognize that we have now a 6-membered ring. And we normally draw 6-membered rings as hexagons. So we just want to start with drawing a hexagon. Actually, I'll use a different, it's really important to get our arrows and our nomenclature right in organic chemistry. So 3 lines is an equivalent sign. So this is just drawn another way as a 6-membered ring as a nice hexagon. It shows much more appropriate sort of bond angles than we have in the other structure. And then if we want to put our numbers in again, we've got 1, 2, 3, 4, 5, 6. And then we can just look at our previous ugly structure and what is bonded to each one of those atoms by number. Okay, so the number 1 carbon has a 2-carbon substituent, what we call an ethyl group, attached to it. So if it has an ethyl group attached to number 1, we can just draw in our ethyl group. The number 2 position has a methyl group attached to it. So we can draw a methyl group in. And then finally, we've got to get that positive charge in the right place. So that's on the 2 carbon. Okay, so we've just got one last step to do before we get to our final product. So if you have a look back at this very first step over here, we protonate the alcohol by using the hydrobromic acid, HBr, and the leaving group that's kicked out is bromide anion. Okay, so there's some bromide anion floating around in solution. There it is there, Br minus. We can draw in its lone pairs of electrons, and being a halide, it's got 4 lone pairs of electrons. We can just take one of those and make that attack that carbon with the positive charge. Now, there's often a little bit of confusion about where do I draw that arrow going to. What I'm trying to show is the arrow ends up at the carbon to which the new bond is being made. So although I've drawn it there like it's attacking the positive charge, I'm not really trying to show it attacking the positive charge. I'm trying to show it attacking the carbon that just happens to have the positive charge. So you might see this drawn in, say, for example, sample answers, or by the lecturer, or by me if I'm your lecturer, attacking from the other side. And it means just exactly the same thing. We're just getting a bond between that bromide and the carbon that has the positive charge, and that will get us to the final product. So it's a cyclohexane with a bromine at that position, and a methyl group, and an ethyl group. Now, what are the important features of this particular question? So in an exam situation, this is asking, can you spot that an alcohol is converted to an alkyl bromide with HBr? Can you spot that would normally go via a carbocation if a carbocation can be formed? So in other words, it wouldn't be likely to happen with methanol because methyl carbocations are really unstable. But with secondary or compounds that can form tertiary carbocations, it's likely to happen. And then to spot that you're going to get a carbocation rearrangement before the nucleophile can capture the carbocation. And then the final little trick here, and this is how you get full marks for the question, is to recognize that when the carbocation rearranges, it can be either the methyl group that migrates, or it can be the primary alkyl group that migrates. And the primary alkyl group is better at migrating because it can support a positive charge or a partial positive charge. And also, that ring expansion and going from a 5 to a 6-membered ring is a good thing. So we get slightly better bond angles in a 6-membered ring than a 5-membered ring, so there's slightly less strain. So if you were, for example, in a quiz or exam situation, if you were to draw the methyl group migrating like that, then you would get a different product. You would get something that goes via carbocation that has a 5-membered ring still and has the methyl group out there and the carbocation in that position. And if you drew that and then you captured that with bromide, you would end up with a different product. And normally I think you'd be expecting to get partial marks for that answer because you've spotted that a carbocation is formed and that it rearranges, but you haven't spotted that the rearrangement is more likely to occur to give a 6-membered ring with migration of the primary alkyl group rather than the methyl group. Okay, so that's about all I wanted to say about that question. And hopefully that helps you with that style of carbocation rearrangement.